Okay, so welcome back. I love this starting exactly on time thing. It's really. So this morning we talked about the pack learning model. We saw an example of a learning model, and I would argue that the pack learning model, at least to some degree, captures what it is that we want in learning. You want to be, or at least that kind of learning. You want to be able to take a bunch of examples, random examples, and come up with a prediction rule that will accurately classify new examples. So what I like about it is that it does get at that core learning problem. And we saw one example of a pack learning algorithm for a very, very simple case. And even for that simple case, we had to work, well, not very hard, but fairly hard to come up with a proof. And so you could imagine how painful and tedious this would be, that every time a new class comes up that you want to work on, you have to come up with a completely new proof. So clearly what we want are general techniques that we can apply to a much broader set of settings, And also, the hope is that by getting these general techniques or results, that they'll also tell us something about learning in general. So, as usual, we want to start with the simplest cases and work our way up to the more complicated ones. So, maybe the simplest case is where the hypothesis space that we're working with is finite. So that's what I want to start with today, is to give a general result for when we're working with a finite hypothesis space. A result that says that all you need for pack learning when you're working with a finite hypothesis space is to have enough data and to be able to find a hypothesis, any hypothesis, which is consistent with the data that you've been given. So it's really an argument that consistency, which we saw intuitively is useful for learning, that consistency is sufficient for learning. Okay, so all right, so first of all, with these pens, if my writing becomes illegible, please let me know. If it's too small or not dark enough or whatever, please let me know. So let's see, again, the case is where we're working with a hypothesis space, and the hypothesis space is finite. And what we're going to prove is a theorem. And so this theorem is saying, suppose we have an algorithm, A, that finds a hypothesis. Let's call it H sub A for the particular hypothesis that this algorithm comes up with, in this class H, which is consistent with M examples. By M examples, I mean, random training examples according to the model that we had before. Coming from a distribution D and so on. Okay, where M is, and we're going to give a specific bound, 1 over epsilon times log cardinality of H plus log 1 over delta. Okay, then if we satisfy all that, meaning we can find a consistent hypothesis and we have at least this much data, then the pack criterion is satisfied. So the pack criterion, again, is that the probability that the generalization error of this hypothesis output by the algorithm is more than epsilon should be at most delta. I mean, I could write it either way. I think I wrote it the other way before. That probability that the error is at most epsilon is at least 1 minus delta. It's exactly the same. Okay? So this is telling us that if we want to get a given accuracy epsilon, then this is how much data that we need. But whenever you see a bound like this, you can always turn it around the other way and turn it into a bound that says, well, if I have this much data, if somebody just hands me this data, what kind of accuracy can I get? Can I guarantee? Yes?
Whenever you say consistency, that means bounded error or?
Consistent just means that this hypothesis perfectly classifies all the training examples, makes no mistakes on the training examples, okay? We'll talk about the more general case later. Okay, so we can state this in an equivalent way to say with probability, where the probability is over the random training set both here and here, so with probability at least 1 minus delta, the error of this hypothesis, the generalization error, is at most log size of the hypothesis plus log 1 over delta over m. Okay, so again, this is just turning things around and saying, if you're given m examples, then the error will be at most this. Okay, it's completely equivalent to this. Yeah?
Earlier you said we were taking the probability because h was a random variable. So the probability on the outside was because h was a random variable. Now are we fixing h? Is that what?
No, h is still a random variable. It's a good question. Always want to be thinking about what's a random variable. So h is a random variable because it depends on the training sample, which is random. I mean, the algorithm might also be randomized, so that could introduce randomness too, but let's not worry about that. Other questions? Okay, so this bound, with either of these bounds, which are equivalent, these bounds are a lot like what we had before. You know, when we were working with positive half lines, we had a bound, a sample size bound that was similar without this term. Okay, so what's new now is this new term, this log size of the hypothesis space. And I would argue that this is our first reasonable complexity measure of how complex the hypotheses are in the space H. So when I say complexity, I know the word complexity has so many meanings in computer science and lots of other places. When I say complexity, I just mean the opposite of simplicity. Okay, now what I mean by simplicity is not so clear. But complexity is the opposite of simplicity. And what we're looking for, one of the things we're looking for, is a way of understanding this notion of simplicity and complexity, or of measuring it. And so I would argue that when you're working with a finite hypothesis space, this is a reasonable measure. So why is it a reasonable measure? Well, intuitively, how do you measure complexity of something like a computer program? So why a computer program? Well, you know, a hypothesis is just a rule, a function that maps new examples to predictions. And in many cases, it literally can be a computer program for mapping instances to those labels. Now, when you think about a computer program, a reasonable, if rough, way of measuring the complexity of the program is just how long it is, how big a program it is, how many lines of code you need. So in the same way, if you're describing a concept, you know, some notion of how complex that concept is how much you need, how many words you need to describe it, its overall description length. I feel like this could be a basis of like gerrymandering districts or something, but yeah. Anyway, so the idea is that description length should be a reasonable measure of complexity. So a description is kind of like giving a name. Like if you write down a program for a function, you're kind of giving a very long name to that program, which is basically all the code that exactly describes it. So if we have a class H that has some cardinality, and we want to give a name, a unique identifier to each one of the hypotheses in this class, how many bits do you need to do that? Well, if you want to give each hypothesis its own name, the number of bits you'll need will be like log base 2, I use LG for log base 2, of the number of hypotheses in the class, right? To give roughly, ceiling of that or something. So this log base 2 of the cardinality of H is kind of, roughly speaking, intuitively speaking, the description length of each one of these hypotheses. So when we look at this log, which is just off by a constant factor, we can also think of it as description length, and in that way, kind of a rough, intuitive measure of complexity. Okay. Also, one other thing to say about this bound is it's the first result that we're talking about that captures those three conditions we need for learning. Those three conditions, again, were have enough data, fit the training set well, and use a simple classifier. So here, we're saying we can get an accurate classifier with error at most epsilon if we have enough data, and if we fit the data well, here we're assuming that we fit it perfectly, and if we somehow bound the complexity. And here we have a specific way of measuring complexity, and we're saying that the result is saying the more complex the hypotheses we're working with, the more data we're going to need to get accurate predictions. So we want to limit that complexity. Okay? Okay, questions on that?
We also have the notion of complexity that also talks about like number of parameters. So let's say if I have this hypothesis of like 2 parameters and like 10
Hold on
parameters.
to that. Yeah. We'll make this somewhat more general. Okay? Okay. Other questions? So I promise I won't say it. That's for every question. But yeah, go on.
Can you give an example of the finite office space? Or is that
Oh,
more of a toy model?
On the problem set, you'll see an example. Okay? I would like to do an example. I just don't have time. So I put it on the problem set. Yeah. Yeah, good question. So what about the concept class? This is all about the hypotheses. What happened to the concept class? The concept class is gone, right? So if you didn't like that concept class thing, we've already kind of dropped it. It's only like an hour later. So the result says it doesn't matter how the data is labeled. All that matters is that you're able to find a hypothesis with it which is consistent. So if somehow you can find a consistent hypothesis, it will have low error. Oh, that's a great question. It's going to be on tomorrow's problem set. Yeah.
Does this connection between training examples and complexity generalize to infinite hypothesis spaces?
That's going to come after this. So we're working our way up. Okay. Okay, good. So I can't prove everything in this course, but I want to give some proofs, which will limit how much I can cover, but still, for math for ML summer school, I feel like we have to give some proofs. So I do want to give a proof of this. We're actually going to prove this in a slightly stronger form. Okay, we're actually going to prove something a little bit stronger. So here's the theorem we'll actually prove. So again, assume given the same number of examples that I had over here. That part's the same. Okay, so then with high probability, which means with probability at least 1 minus delta. Okay, so here's the part that's different. We're going to show that for every hypothesis in the class, if the hypothesis is consistent, to save writing, I'm just going to write cons. That just means consistent if H is consistent with the training set. then that H, that hypothesis, has error at most epsilon. Okay, so it's almost the same thing. Here we're just proving it about one particular hypothesis, the one which is the one found by the algorithm. Here we're actually proving it for all of them. We're saying for all of them, if that hypothesis is consistent, then it has to have low error. And if we can prove that, then this follows, because we're assuming the algorithm can find a consistent hypothesis. So whatever one it is, it's in this class, and since it's consistent, it has to have low error. Okay? So we're going to prove this slightly stronger result. And I can write this in symbols. Oh, first of all, it's common when you say the error is at most epsilon, it's common to say that H is epsilon good. And if that doesn't hold, it's epsilon bad. Okay, so we're saying that in symbols, for every H in the class, if H is consistent, that implies, which is the same as if then, that H is epsilon good. The probability of that whole event should be at least 1 minus delta. Okay, so this is just rewriting this in symbols. Okay, and what we will actually do is prove that the probability of the negation of this is at most delta. Okay, so this is the same as this, and this is the same as saying the probability of the negation of this. So if you negate this whole thing, that's saying there exists a hypothesis in the class such that the hypothesis is consistent. It's kind of a counterexample to this. A hypothesis which is consistent, and, that means and, the hypothesis is epsilon bad. So we want that probability to be at most delta. Okay. Are people familiar with implication? Hopefully. Okay. As a logical operation? Okay. Okay, so that's what we want to prove. Okay, so what's the idea of the proof? Here's the idea. Let's just think about, oh, I'm trying to get the cap off. There is no cap here. Okay, let's just think about one single hypothesis. Okay, one hypothesis, which happens to be epsilon bad, which means it has error, generalization error more than epsilon. Okay? And to make it really concrete, let's say epsilon is 1%. So this thing has more than 1% probability of misclassifying an example. So now, suppose we take several hundred examples. Our training set consists of several hundred examples, and each one has a 1% probability or more of being misclassified. So in a sample of several hundred examples, the probability is overwhelmingly large that at least one of those examples will be misclassified. So the probability that that one hypothesis, which is epsilon bad, will be consistent is very, very small. And then we just have to take that argument and repeat it for all the hypotheses in the class. Okay? That's the whole idea of the proof. So let's see how to do that. Okay, so again, we're trying to prove this, bound this. So here we go. Okay, so probability that exists, I'm just copying. Okay, it just copied. Okay, so let's see. It's useful to pay attention to the random variables and what things are random and what things are not random. Okay, so whether or not H is consistent, is that random or not?
given training?
It is, because the samples are.
Yeah, the only thing that's random is the sample. And so really the question is, does it depend on the training sample or not? Whether or not this one particular hypothesis is consistent, that definitely does depend on the sample, right? It's whether it's consistent with the sample. What about this, whether it's epsilon bad or not?
No.
That does not, right? That does not. So either the hypothesis has generalization error more than epsilon, or it doesn't. It just does or doesn't. It has nothing to do with the sample. Okay? So this is not random. So what we can do is we can define a set, let me call it B, which is just all the hypotheses in the class, which are epsilon bad. Okay, this is not a random variable, because whether or not a hypothesis is epsilon bad, it just is or it isn't. So this set, the learning algorithm has no idea what it is, but as mathematicians, we can write it down before seeing the sample. And then with that little bit of notation, we can rewrite this as the probability that there is a hypothesis in this set of bad hypotheses, which is consistent with the training set. Okay? Okay. So when we have this there exists statement like this, that's really just like a great big or. Okay? It's like there exists a hypothesis, a bad hypothesis, which is consistent. That's really the same as saying, is the first hypothesis consistent, or the second hypothesis in that class is consistent, and so on. So we can just take this there exists statement and rewrite it as a giant or. This is like a great big or, like you would do a summation, but this is an or instead, over all of the bad hypotheses that they're consistent. Okay. And now when we want to compute the probability of an or, we can use this really simple bound called the union bound, which says the probability of an event A or an event B happening is always at most the sum of the probabilities, probability of A plus probability of B. And this is called the union bound. Might have other names in other fields, I don't know. And it's always true. You don't need independence, you don't need disjointness, you don't need anything. It is always true. So we can apply it here, and we'll get that this is at most, we're doing probability of a giant or, so that's at most this giant sum over all hypotheses of each one being consistent. Okay? So now, for a particular bad hypothesis, we have to compute the probability. Oops, I lost probability, sorry. Yeah, is that what you're going to say? Okay. Okay, we just need to compute this probability of it being consistent. Okay, so let's do that. So let's pick one particular hypothesis H in this set B. So it's a bad epsilon bad hypothesis. So we're fixing it. So we're picking one particular one. It's not random. We're picking that one particular one. And we want to compute the probability of it being consistent with this sample. Well, what does it mean for it to be consistent? Well, it means that this hypothesis should correctly classify the first example, and it should correctly classify the second example, and so on. Okay, its prediction should agree with the true concept C. So I just wrote out what it means for it to be consistent. Now we can use the fact that these examples are independent. each of the training examples are independent, just like we did before in the proof this morning, and write it as a big product. And what is this probability? Sorry?
1 minus epsilon.
1 minus epsilon, okay, because?
There's an epsilon chance of making error for that.
Right. The probability of making a mistake is at least epsilon, so this is actually at most 1 minus epsilon, or maybe strictly less than, I don't know. Okay, so this whole thing is at most 1 minus epsilon to the m. So coming back over here, each one of these probabilities is at most 1 minus epsilon to the m. And we just add it up over all the hypotheses in B, so we get the cardinality of B. The cardinality of B is at most cardinality of H. And maybe I should. So this whole thing is at most cardinality of H. And again, we can use that bound that says this is at most e to the minus epsilon m, just because 1 plus x is at most e to the x. And then by our choice of m, this is where our choice of m comes from. If we pick m like this, then this will be at most delta, which is what we wanted to show. Okay. Questions on that? You guys are like real mathematicians. Do real mathematicians actually write QED at the end? I always want. Computer scientists, they're boring. They just put like a little box. Yeah. Yes?
So haven't we actually shown that the probability something is consistent is very low, regardless of it being good or bad?
No, because we use the fact that these are epsilon bad. Okay, so in the proof over here, we fixed an h that was epsilon bad.
So that's why we have the 1 minus epsilon.
Exactly. Other questions? Yep.
Improve the bound because like you did actually, because basically the size of B is where the right bound is there. So is there also like, if you could comment on how can you improve that?
Oh, well, yeah, I guess this automatically gives you a bound in terms of the size of B. That's true. But, well, it's just harder to, you don't usually have that information ahead of time, so it doesn't help you that much. But yeah, I mean, it's giving it to you for free. That's true. Okay. Okay, good. All right, so this question of how to extend this to infinitely large hypothesis spaces has come up a few times. We're clearly going to want to do that. The one example I gave was for an infinitely large hypothesis space. So we know that it's at least sometimes possible when you have an infinitely large hypothesis space to do pack learning, to achieve the pack learning criterion. So there must be something about those classes that makes that possible. So what is it? What is it about those classes that make it possible? So let's see. So let's go back to that one class that we know about. I've heard this stuff is addictive, though. That's the thing. That the board gets addicted to it, and then you can't erase at all without it. But I guess that's not my problem. Okay, that's pretty good. Okay. Right, so we talked about one class where it's infinitely large, and yet pack learning is possible. That, again, was this class where the examples are on the real line, and every hypothesis or concept is defined by a threshold, above the threshold positive, below the threshold negative. It's clearly an infinitely large class. There's no question about that. But think about just how this class behaves on a finite sample. So let's suppose our sample consists of just 4 points. So of course there are infinitely many hypotheses, as I said, but a lot of them seem kind of redundant. Like this hypothesis gives exactly the same predictions as this other hypothesis. Hopefully you guys know what I mean by these different pictures, the hypotheses defined by these thresholds. So those classify those points exactly the same. And in fact, if you think about it, for a sample consisting of just 4 points, there really are not very many behaviors that are possible. In fact, we could just list all of them. So for instance, we could have, I have a hypothesis like this one out here, which classifies all 4 of the points as positive. So this is supposed to be the classification of this hypothesis on this point and this one for this point and so on. Let's call this H1. Okay, and likewise, you immediately, I'm sure, can see what the pattern is here. There's another hypothesis there, H2, which classifies this one negative, positive, positive, positive. And just for completeness, let me list all of them. Okay, H3, and then we could have another one like this one, H4, negative, negative, positive, and then we could have one way out here that classifies everything as negative. Okay, so that's it. Those are the only possible behaviors that we can get using hypotheses of this form when you have a sample, in this case, of 4 points. And in general, if we have a sample of m points, if we have a sample of n points, then how many behaviors? We would just get m plus 1, right? M plus 1. So how does that compare to the number of behaviors that are possible? So the worst case number of behaviors that are possible on m points would be, well, more than that. 2 to the m, right? You could get, each one could be either plus or minus. So you could get 2 to the m behaviors. Behaviors, these are sometimes called behaviors, labelings, dichotomies. So the worst case is 2 to the m. And here, with this hypothesis space, there are only m plus 1 behaviors possible, which is really tiny compared to the worst case number of behaviors. So in these nice cases, like this one, we're only getting a polynomial number of possible behaviors on any training set. So kind of the intuition that we're hoping for is that somehow, given a sample m, we can kind of treat these hypotheses or these labelings as forming a kind of effective hypothesis space, forming a kind of effective hypothesis space, and work with that effective hypothesis space rather than the full hypothesis space, and somehow get bounds out of that. Yeah, question?
Just for clarification, because I kind of raised this question last time. So a polynomial number is just that number raised to a finite, or not necessarily finite, but to a power rather than a power being raised.
Right, correct. So polynomial means like this. So in general, I mean m to the d, yep. So by polynomial, I mean O of m to the d, where this O is just hiding a constant factor, okay? And d is a constant. Good. Okay. Okay. So, So we can make this more formal. Let's go crazy, man. Okay, we can make this more formal. So we can, for any particular hypothesis, and okay, so if we have a set S, like this one, which consists of a set of examples, instances rather, what we can do is we can write down the behavior of any particular hypothesis on that sample. So it'll just be a bit vector, which is the prediction of H on the first one, and so on each of the M instances. Okay, so for a particular H, what I wrote down so far is just exactly one of these vectors. And then we can list all of them over all possible hypotheses in this space. And what we end up with is a set like this, a set of these bit vectors. Right? So the notation for that is pi sub h of S, where S is this set up here. Okay? Or really it's a sequence, but it doesn't really matter. Okay? So this is the set of possible behaviors or dichotomies or labelings. And then we can look at how bad this set can be, how large it can be for any sample of size S. So we can, with a little bit of overloading, we can say for any size M, we want to know what the maximum cardinality of this set of behaviors is over all possible sets S of size M. Okay, so like in this case, this number would be M plus 1. And this is called the growth function. Okay, so the idea, or the hope, or the wish, I should say, is to take a bound like what we proved before for finite hypotheses and apply it somehow to these labelings, to treat them as kind of an effective hypothesis space, as I said before. Okay, so what we showed before was we said, given M training examples, as usual, I'm kind of writing it in a little bit more abbreviated form, with probability at least 1 minus delta for every hypothesis in the space. If that hypothesis is consistent, then its error is at most, so I'm taking what we had before and writing it in this other form where you're given a certain amount of data and you can say what the error is. So what we had before was that this would be like at most log cardinality of H plus log 1 over delta over M. So this is what we proved before for finite hypothesis spaces. And now what we wish we could do is, instead of using the actual number of hypotheses, which is infinite here, we wish that we could use the number of behaviors on a finite sample, or at least its worst case bound, which is the growth function. So what we wish is that we could put the growth function in here. Now, in fact, that is possible. Well, it's possible if you play around with the constants a little bit. So if you throw in, rather than the growth function on a set of size m, you make it 2m, and then you have to play with these other constants as well, but let me just use big O notation for that. Okay, so in fact, it is possible to prove a theorem like this. Yeah?
Can you explain the purpose of the max in the growth function?
It's just to get a worst case number for any sample of a given size. Okay? So like in this case, to use m plus 1. It's just to give a worst case number based on the number of samples m. Okay? Now, the reason a bound like this is interesting is because, as we said, in the nice cases, this growth function will only be a polynomial. So in particular, if the growth function is O of m to the d, a polynomial, then what does this bound give us? Well, when you plug in, by the way, this is all inside the log here. Sorry. When we plug in this to this bound, what we're going to get is a bound that's like, that the error is at most something like d log m plus this other stuff over m. But the point is that we're still getting this nice bound, which in terms of m is like log m over m, which is going to 0, well, not quite as fast as 1 over m, but still pretty good. Okay, so this is the nice case that we wish for. Is this making sense? Okay, so, so this is an actual theorem. We're not going to prove it, but let me say a word about it. So we wish we could use the proof that we gave before. But the problem is that in that proof, we needed to specify the hypotheses that we were working with before any data was actually generated, before seeing the training set. So here, we want to be working with this effective set of hypotheses. Like really, we'd like to be working with something like this, with like just this one representative for each one of these labelings. But the problem is that these depend on the training sample. So you can't say what your hypothesis space or your effective hypothesis space is until after you've already seen the data. But at that point, you've kind of ruined everything, because then everything is dependent on everything and it's a big mess. So the whole proof kind of falls apart. So you need to use a fancier technique. We're not going to give a proof of it, but tomorrow I'll give a proof of something that's sort of more general. Okay, so we'll see a proof that's sort of more general and that uses some of these fancier techniques. Okay, yeah.
One question. So on the left side of the example, you have a nice behavior of m plus 1 is because all those x are sorted, right? But in general, if you generate those x from a distribution randomly, then those x are not sorted anymore. Then
it doesn't matter about the sorting. The sorting doesn't matter. It's just counting how many possible behaviors there are. If I permuted columns, that wouldn't change the overall number of labelings that you could get, because we're just counting up all possible labelings on these points. Okay, so the sorting really doesn't matter. Does that make sense? If you just reverse these, you would get not as nice a bit pattern, but there would still be m plus 1 of them. You look really disbelieving, but
So
yeah.
to get m plus 1, you need to have this monotonicity of the hypothesis space, right?
You need,
You cannot label the first plus, the second minus, the third plus, etc.
okay, this is true for positive half-lines. Okay, it's not true for any hypothesis space. Okay, so maybe that's what you meant by the sorting. I'm not sure. Okay, so for other classes, we'll get a different number of labelings. That is most certainly true. Okay, so this is like a really nice case. Okay, and this is a really terrible case, 2 to the m. Okay, and the question is there stuff in between? Yeah.
Yeah, have you ever seen any hypothesis that with a growth function to do that?
Yeah, so we're going to talk about that. Okay. Yes?
So the growth function depends on how you define the hypothesis space.
Yes.
And the hypothesis space should be defined with the assumption that H can be consistent, right?
This is true for the hypothesis space. Okay, so if you look at the definitions here, the actual concept, the truth, does not enter into things. It's only talking about the behavior of the hypotheses on unlabeled examples, on the unlabeled instances. So in the theorem, yes, in the theorem it does involve consistency. But the growth function does not. The growth function is only talking about the behavior of the hypotheses themselves.
If a hypothesis that cannot recover the true mapping or cannot give a good approximation, then what's the meaning of that hypothesis space?
So this kind of a theorem, it's saying that if there's a hypothesis that's consistent, then it has small error. But if the hypothesis is not consistent, it doesn't say anything. So it's possible that none of the hypotheses are consistent, in which case this theorem is completely vacuous. Okay? Yeah. Good. Okay, so I think it's worth taking a step back and looking at what's going on here, because I think it's an important thing. So we started with a question about probabilistic learnability. Learnability in this model where all the data is random and the test examples are also random. And we wanted to prove something probabilistically about performance. So it was a question that seems to be all about probability. But what these kinds of results tell us, as well as the one before for finite hypotheses, is that no, all that really matters are combinatorial properties of the hypothesis space that we're working with. So if you're working with a finite hypothesis space and you're able to find a consistent hypothesis, to show that it has low error, to show that it's a PAC algorithm, all you have to do is count. You just have to count how many hypotheses there are. And when you're working with infinite hypothesis spaces, like over here, again, the question boils down to a combinatorial question, a question that involves counting combinatorial properties of the hypothesis space itself. Okay, and that creates these very general kinds of results. All right, so let's drill down more on this growth function. So as I said, maybe, God, every time I have to erase, I dread it. Okay. As I said, there are at least some nice cases where the growth function is polynomial. So in these nice cases, the growth function is like O of m to the d, where d is a constant. I say it's constant, but of course it might depend on the hypothesis space itself. So that's the nice case. And in the worst case, this growth function realizes all possible behaviors, okay, which means that there exist samples where all possible labelings can be obtained. So the growth function would just be 2 to the m. That's the worst case. And it's reasonable to ask if there are any other cases. Are those the only cases? So it's this amazingly beautiful combinatorial fact that these are the only 2 cases. These are the only 2 cases. So for any hypothesis space, H, either we're in the first case, the worst case, or we're in the second case, and there are no other cases. And what's more, this dichotomy of the 2 cases exactly corresponds to when learning is possible. So when we're in this case, when I say learning, I'm ignoring computation. Learning in terms of how much data you need. So when we're in this case, in this nice case, as we saw over here from this theorem, learning is possible. We can quickly drive down the generalization error. And when we're in this case, learning will not be possible. Okay, yeah, question.
Do you mean for a problem where data gets a binary label? I mean,
Yes,
okay,
yes. Subject to all the assumptions we've made so far, yeah. And for pack learning.
And if you allow 3 labels, then that's 3m. But
Then
it's
it's-
exponential or polynomials.
You need other definitions, yeah. Yeah,
So in the worst case, it's like literally 2 to the m, not like O of 2 to the m?
correct. Literally 2 to the m. Yeah,
Oh, you mean?
sure.
Oh.
Somebody go.
So in the case of now with more generalized case, how do you bound the least number of examples that you need in terms
This
of
case? No, you can't.
in terms of the growth function before we have ln of the cardinality of the.
So what happens in this case? In this case, learning is not possible. You can't learn. This is where learning you can do. So this dichotomy corresponds to where learning is or is not possible. Learning meaning pack learning, blah, blah, blah. Okay? Did you have a question? Oh, somebody, yeah?
The assumption now is the target class is finite, right?
No. This is for all hypothesis spaces. Wait, the concept class? The concept class basically doesn't enter into the picture. Okay, because we're talking about results of this kind. That just says if you can find a consistent hypothesis, then you can get this kind of error. And we're going to generalize this more later. Okay?
This class will kind of be
For the hypothesis space, this is for all hypothesis spaces, finite or not. If you're in the finite case, you're automatically in this case. Because then this is a constant. Because it's finite. Yeah, it won't depend on m then. Yeah.
Learning is always possible in a nice case.
Learning in this sense. Okay, which basically means the pack case. Okay, so yeah, learning where you have an algorithm that can find a consistent hypothesis. It's saying you can get bounds that say you have enough data for learning. That's what I mean by learning. Okay? Yes, that's what I'm going to do next. Now I'll segue into the next question. So how do we show this? Okay, well, it turns out that this constant d, this exponent, is something really special. It's a special combinatorial parameter that's called the VC dimension, which is the last topic I hope to talk about today. Okay, so it's going to turn out that this exponent is the VC dimension. Okay, VC obviously stands for Vapnik-Chervonenkis. I knew everybody's on the tip of your tongue. Vapnik-Chervonenkis dimension. Okay, VC dimension. So let me explain what VC dimension is. Before I can say what it is, I have to say what shattering means. So if we have a sample S of m points, okay, a sample S of size m is shattered by a hypothesis space H that we're working with if all behaviors are possible. Okay, so if you're in that worst possible case for this particular sample, all behaviors are possible. Or labelings, all possible labelings. So formally, that means that if you look at the set of labelings on that sample S, the number of labelings will be equal to 2 to the m, because you get all of them. Okay? So, for instance, I did not factor in enough time for it. Shit. Sorry to spend so much time erasing. Okay, for instance, let's talk about a new class, the class of intervals, which just means domain are the real numbers, and a hypothesis is positive for points in some interval and negative outside. So if we have 2 points, like this one and this one, then I would say that these 2 points are shattered, because if I give you any labeling, and there are only 4 of them in this case, like plus minus, then you can find a hypothesis of this form that realizes that labeling, like this one. Okay? And you can do that for all of them, right? So if you have plus plus, you could have that. Minus plus, we could do one like this. And then minus minus, we could do one like this. Okay, so this set of 2 points is shattered. Now what if we had 3 points? Like these 3. Are these 3 points shattered? Okay, why not? You cannot get plus minus plus. If you try to do plus minus plus, that kind of forces you to use a really big interval like this one, but as soon to include these 2 positives, but as soon as you do, you can't get a minus here. Okay? So using intervals, it's possible to shatter some set of 2 points, but you can never shatter 3 points. So the VC dimension of a class H is the size of the largest shattered set. The size or cardinality, I'll just call it size, of the largest shattered set. So that little argument we did over there shows that VC dimension of intervals is 2. We know it's 2 because we showed that there exists a set of size 2 that's shattered, and we argued that no set of size 3 can be shattered. So the VC dimension is 2 in that case. Let's see, how am I doing? Okay. So let me talk about one more class. Okay, I won't give a lot of examples, but a really important class is the set of linear threshold functions. So a linear threshold function in Rn is just a function defined by a hyperplane. So that's supposed to be a hyperplane. I guess it's a line in 2 dimensions. And all the points above the hyperplane are classified positive, and all the points below the hyperplane are classified negative. Okay, a linear threshold function, very important class. The VC dimension of this class turns out to be n plus 1. Okay, it needs proof. It's not obvious, but some linear algebra. And if sometimes we want to restrict it so the hyperplane has to go through the origin. So if we do VC dimension of linear threshold functions that go through the origin, this is supposed to be the origin there, then their VC dimension is just n. Okay, I'm just throwing this out because it's a useful fact. So somebody asked about number of parameters. So let me just give a couple comments about VC dimension, and then we'll finish next time. So in all three of these examples, the VC dimension happens to be equal to the number of parameters, if you think about it. So an interval is defined by two endpoints, so it has two parameters. A linear threshold function, if you think about it, has n plus 1 parameters. If you restrict it to go through the origin, it only has n parameters. So it's often the case that VC dimension is equal to number of parameters, but it is definitely not always true. Well, I don't know why I say it so emphatically. They're like these weird counterexamples that show that it's not always equal to the number of parameters, but a lot of the time it actually is. And if the hypothesis space is finite, so if we're working with a finite hypothesis space, then it's not too hard to argue that its VC dimension is at most log base 2 of the size of the hypothesis space, which is our earlier complexity measure. So now this VC dimension is kind of subsuming our earlier complexity measure, which was log of cardinality of H, and it's going to play a similar role, but it's going to be much more general. Okay, so let me stop there, and we'll finish talking about VC dimension next time and other stuff. So nice that you caught the return.